Thank everyone for coming. So I would like to introduce today's first of two speakers, Sara Jabbari-farouji from the University of Amsterdam, and she will be talking about active filaments in complex environments. Please go ahead.
Yeah, thanks. And thanks for us to present. Time that is not so Polish, especially. Ideas, especially the second part is not published yet. So I will talk to you about. And I'm technical, so I show, but I try to make it into experiments when possible, but it's ongoing actually. So just this. I haven't
used to the pointer somewhere, but it's in the other room.
You have a stick here.
Oh, right.
Yeah, exactly. I prefer a switch and actually point. Sorry, I want it to be run. So for me, the motivation of active filaments comes from nature. If you look at from micro scale, there is bacteria which are elongated and they have some degree of flexibility. I think active polymers traditionally starts from a lot from these elements of cytoskeleton, the biofilaments like actin myosin driven, and they were also built in vitro in the carpet of molecular models, and they are self-driven. And of course, if you go to a larger scale, you can think of worms and snakes. And I know it's a bit of simplification to think all of them are similar, but in a way they are filament for me, and they are self-driven. And it has also inspired people. But I don't need to go there. And this is like a chain of colloidal caterpillar, which is inspired by caterpillar, as the name comes. Okay, works. I wanted to move this one, but no, it doesn't work because distance. And so let's see if this one works. This seems it's working because it was in the, but you can type of thing and just chain up the other one. So you can see here is in a chain, so it has rather restricted mode and motivates my work in the complex environments, but in channels. And I made something very slow motion is the actually display. A shell of elastic. I tell you why I see if we can really compare simulations to experiments, but at the moment I don't have that comparison yet. And just to put it for me, active so which was for polymers. Element to that it just he thought about people use this as a model when you as if as I who have worked on this model. Spectrum of models that it can be because it's really nice by program. So, but today I tell you my motivation comes model system that my experimental work. One is the worm. I'm such a really. Oh, it doesn't. I think because it doesn't have video here. So it's the worm that is at the first order after. Anyhow, it looks to us that it's like a good, could be a good model we are working on. Really, this synthetic system, which is more controllable, have connect the chain of shells. And another thing, so and it's interesting to how this is in different situations. And as I told you, I will start first. There are macro. Small biofilm. And we did a systematic study of this. This is the work done by. And before doing that, I would like to get one slide. And I start from example of Brownian motion. We know that and relaxation one time. The you have to do the simulation sometimes. Now, if we go to the case of active people in Düsseldorf, Christian Scholz and robot. And so this is the equation of motion. Basically, you have an self-proportion force in addition to damping and noise. And you also have an equation. But you don't have active torque. And what they find is that when you have time scales, you have the typical factor, but you also have a time which is the typical for the persistent time. And in this, if you calculate a lot in there, if you calculate score displacement for a Brownian motion, inertial system. And that's inertial.
Why you don't have it? inertial time constant, time unit, time n in this.
You mean here?
Yeah.
This comes from analytical calculation,
Yeah.
not mine. And it's what is interesting that it does not depend on this effect. Have that, it doesn't show change. So they did different mass and no, which you could I know this is coming from calculation stuff.
I understand, right? It's that the center of mass inertia goes away above the transformation inertial scale like in classic calculation. So this is activity coupling the
Yeah.
rotation inertia. Otherwise,
Yeah, exactly.
it would all go away, right?
Yeah, you are right, exactly. Dynamics of NHAT is induced by
Yeah, okay.
by yeah. And now we look at the polymers. Before I go to active one, I just the probably the equation of mass velocity correlation. I have here 1 over n noise, and that's a famous Rouse model of term basically. But now if we make it active, acting so yeah, what happens here, we have an active force in addition to so unit of length. And I show you the I'd like to show you the results of the overdamp case, which is actually looks like very more 2D, but oh, it's a you can see it's really very light motion. So activity. Say I wrote there that this blue spots just vector. So I skip this because you see nothing much happening here. It just continues moving slowly.
So do you see any change in the sort of typical size of a polymer compared to a polymer without activity?
And compare model, we see a very shrinkage. I will show you the result. In the case of the model Bianco, very much stronger. A lot. And then okay, I skip. Show you the case. Inertial one. I'm sure very high active force. Okay. Straight. And then here to answer your question. You can see that active force 0 is okay, it's logarithmic, but we have the result. Inertia was assigned by or at low active force. So swell. Basically the physics of the time scale of advection and the inertia. High active force is time scale of inertial advection becomes very small. Leads to the opening of the collisions. It quickly opens up the polymer.
And is it a constant thermal noise as well, or is it?
Yeah, it is, but we put it quite low. It's at 0.1.
And so the limit active force going to 0 is the thermal limit here.
Yeah. If you are at a low active force, or because it actually I didn't write F star. It has it doesn't have the limit that it becomes like.
Excuse me, do you think there's a clear transition between the two regions?
I mean, but it's more continuous, but for me it's continuous. But a good point I hadn't done in terms of.
Have you varied the length of the polymer?
Pardon?
Have you varied the length of the polymer?
Yes, thank you. You make me ready. Okay, I wanted first to depends on mass into size. Originally, I had usually write. I first show the mass. So that I didn't write. I told you this as I showed mass, and you can see end-to-end distance. Actually, maybe better have had this later. You can see that with the mass, somehow a bit spoils us. But anyway, this is showing that with mass also the effect is stronger the higher the mass is. So yeah, and actually here, yeah, it's for different active forces. But here, as your question, so we thematically for very different, and see is that it's always at the level of. It's not by the whole. Degrees of freedom open up. That's where it becomes. And so there are a few outliers, but it's because cannot copy on it, so then you get a second instability. And so we try to scale all the data together. Flory constant. Case of underdamped is the red one. It's not changing the stiffness because we are doing fully flexible polymer. We don't have any bending and stiffness. And for the case of overdamped case, it's going up the stiffness, and that's what you could see from the video. It's really. going down. Because the scaling so half, which is for the random work. And just to verify this, we can directly calculate the induced stiffness. We can directly calculate the stiffness. Persistence is just you calculate from the bond-bond correlation. You just yes.
Yeah, so I appreciate that when the polymer is undergoing extension due to a force, that the persistence length increases because it's undergoing fewer fluctuations. But does the actual polymer itself stiffen, or does it just look stiffer?
It's much different in terms of conformity.
But it's undergoing an external force. So if I take an equilibrium polymer and then I stretch it, the stiffness of the polymer is still the same. It's just that it's undergoing the external
It's
force.
effective persistence in terms of how we quantify it. But the intrinsic property doesn't change, and that's what I mean.
Got it.
Yeah. But yes.
Do you ever see your polymer curling up in a spiral?
With the two
Yes,
dimension,
you talked before,
you
yeah.
have more degree, more. Actually, originally I wanted to get the effect of bending a stiffness with the same thing.
Sorry,
Yeah.
similar question. This is not the working chain is not self-avoiding.
It is self-avoiding.
Self-avoiding.
Yeah, it is. It is part of that, yes.
The experiment of microtubule
Yeah,
working on the kinesin motor.
yeah,
But
yeah.
the chain makes a spiral.
Yeah,
Because
it's-
it's self-avoiding. But
Yeah.
you don't see it.
You need self-avoidance and two dimensions to
Yes,
spiral.
two
Yeah,
directions.
exactly.
Yeah, this
This work is very nicely displayed by. That would be beautiful spiral. I'm not showing it here with the unit really set. Also, I showed the second part of the quantum model, and then you don't see a avoidance and the two dimension.
Sorry, you said again, the peaks that appear at the towards the very large phase. Can you say again what's happening there?
This one. Yeah, here this is for chain lengths. No, it's easier with this. It's chain lengths 50 and 100, and here my persistent length is almost approaching the chain length, and then I get the instability. I haven't really when the stiffness.
So the
There
other
it goes.
curves should also have these peaks. These other curves will have these peaks.
Yeah, if
Yeah.
I continue active forces. Realistic situations to experiments, because the robots are not as fast as we want to see the inertial effects. So the message is you need to have high enough activity, and robots are a bit more careless. We need drones, chain of drones in 3D.
So what you're saying is that there's some kind of instability that after when you stretch them out,
Yeah.
they sort of cut, they kink and start
Yeah.
bending.
Yeah.
Is that what you see?
Yeah, yeah.
Okay.
I don't have any, but we are good. But if you know how to interpret it, would be nice. We didn't understand.
Okay.
Yeah.
So
And then,
we can chat about it later.
yeah, would be nice actually. I a bit gave up because we couldn't see any experimental system with the series, but it's interesting physically. I get why. It's funny phenomenon. I'm just showing you. Now I want to show on the line. Here, I first draw your attention. So this is as a function of active force, the long time diffusion, which means when you get MSC at very long time, and you get the slope. So this is the case for the passive case, and by D0 I mean the passive diffusion coefficient. Okay, and what you can see for the overdone case, they all they really obtain this by solving the house model for them. And the other case, you see, again, everything almost falls on the same curve, apart from these instability points, which happen for short chains. But you see clearly a more advanced, a more enhanced diffusion compared to the case of Brownian robot. Additional enhancement because of active. Understand it?
I'm missing something here. So why doesn't it converge to 1 on the left side? If you say that's the
Oh, sorry, then I made a mistake. It's not the diffusion.
Ah, okay.
It's 1 over empty. Sorry.
Okay.
Okay. Because no, I think so, because the 0 we defined was in this equation. Yeah. Anyhow, yeah, it's the. You are right. It's because of that we decided that we keep the same. Otherwise, is oh, what? I went too far. And then I go further. No, I think it's really, yes. Okay.
Yeah, please. You can
So, and then the question was how we can understand this enhanced diffusion because of inertia. And then we said we just do a typical. You need to equations of every pore. Get the damping factor, and then you get the sum of total active forces and total random noises, and you know the property. And then from this you can calculate velocity correlation function equations. I made a mistake in integral, but he did. And then we obtain that when you do this and you take the line time limit, because you want to have especially then you find that the velocity correlation has an exponential part, which is again the same relaxation time, which is the inertial time scale of the monomer, the same as the passive case. And then there is a new contribution, which has a bit fun because it depends on this can for the tangent driven polymer. Any force y on the that this contribution of active force has a contribution from the force correlation. Yeah? So this is just the force time. So it's the integral modulated by the exponential of relaxation. If you have this diffusion, and so for us the problems we don't have it yet. I think it's doable, but we haven't. But you need to but at least in the biolinear group they use a non-Hermitian mechanics. It's actually quite nice mathematics, but I haven't done it yet. So basically for now we just calculate we need to calculate the end-to-end vector correlation. For now we just results, and this is the results I show here for both overdamped and underdamped. So this oscillatory one, the field symbols are for the underdamped and the triangles are for the overdamped. And you can see they are quite similar. The only just has a bit of more oscillation, which you expect because of inertia. Relaxation time is we can see the trends that the is quite calculation. So this is nice that it has a simple scaling. This is 1 over to n FA. So that's one message from active polymer. And in the Rouse model is n, so it's much less faster than the passive one, but also it this beyond like FA 0.01. So of course at some point it breaks if you are very low activity that push the passive limit.
You see, in this limit, would it be possible to also look at direct spatial correlations
Of what?
along the polymer?
You mean the bond-bond correlation?
Things like that, yeah.
But in time, you mean? Because
In space.
in a space, we have a bond-bond correlation, that's when we got the persistence out. But it's
Yeah,
not
okay,
dynamic
sure.
quantity.
Okay, sorry.
I didn't want to show it because there was a bombardment with. I don't want to. It agrees per just the way equations are correct, working for this smaller system. And then the good thing is that, as I told you, once correlation function and calculate the line time difference. But the point is, what we realize that end-to-end vector is quite similar, passive, and it boils down everything that the difference of the line time diffusion of inertial polymer come from the. I need to go. Maybe I went too quick because here I had end-to-end vector correlation, but we can just take RE square out because the fluctuations are small. So change here. Yeah. And so that's why if I get that, then it's quite similar, this contribution. And then we could. And the end-to-end vector was much bigger, and that explains comparison of the theory and experiments. So there are many symbols, so these squares are from the theory. It shows a very good agreement. We have some errors in the computation of correlations numerically, but overall it shows a very good agreement. Yeah. So I think what I wanted to tell about inertial. In that case, polymers and persistence and fusion. So basically, you finger.
If you make your orientational noise strong enough, could that break the inertia and then bring you back into something similar to the overdrive case? Or
Orientational noise of what?
so if I remember right, it's the activity couples to the orientational inertia, not to the translational inertia. And so can you break that by adding a lot of rotational noise?
Yeah, actually this. And then when the noise on every is uncorrelated.
Okay.
And for this, I don't show a paper. Then if you have only mass inertia, but you need to have rotation because you already. But that's why you are not pushing it yet. But the point is that I almost do this analytically. But we know you need to have a sufficient large number.
The experiment on what it was, what it changed.
Yeah, the ones.
Is it 2D, I think?
No, actually ones are 3D, but I'm just gonna switch. FA is the total mass. So it's too But also,
Can you comment a little bit on technical details? What's the model for the bond and what are the integrators used in both cases?
we use the model of Gomper exactly, that the monomer is the sum of the two bonds.
No, but for the bond, the finite bond or is
We use the technical point because we really
and the integrators?
we use the Brownian integrator for the ED part for the overdam, and Rajava integrator for the. Now I go to the second part, which is again coming in Amsterdam. They just are putting the worms. They make it glass pillars, and they put the worms bigger in between this, and they can see what sort of run. Yeah. And so I start showing the just. You can see the 3D of the 3D worm.
Okay, so first thing is that these are these worms you showed at the beginning. These
Yeah.
Yeah.
It's the aquarium worm to be fixed.
Okay, and what are you so how high are the pillars?
Bottom.
Okay.
I mean, they go a bit up when they get problem with obstacles.
Yeah, sometimes I see the trajectories going through the posts. Is that because they actually go crawl over the post, or?
Yeah, I think they can a bit go. Actually, I don't remember. I have seen them, but they are not so high. The thickness of them. So I think
I couldn't imagine this to be such.
but they were like I think a few centimeters, not 2 centimeters, but
They seem to be also enjoy wrapping around them.
yeah. And this we can also see sometimes are you see it from the simulations. It is wrapping was very strong when they were on the floor, but I don't have simulations on the floor yet. I think it's so just it's part of that we do model, so we use the same thickness of so if I choose the monomer size for the obstacle, so it's quite bigger. And as I told here, I do 2D in this or the excluded volume. And just to be clear, excluded volume otherwise it doesn't matter actually anyhow. So and then that case you would get a spiral that I will not show you because I have time for model. And then I will there is one thing, some basic and the bending is the angle between the consequent bonds. And so in 2D, in this model, is a more steep. And okay, divided by KBT, but and the degree of flexibility can be basically all the simulations I show on from now is for a fixed change 100, yeah. And just to get your attention, I show you here the results. I wanted to show this. Okay, it shows both of them the same. Non-time you go rather straight like, and we wanted to look at. But I show you here a relatively low packing fraction % of the obstacle, and you can see from the movies, actually not much happening. So I will show you, but I will not focus from the free space because the obstacle spacing is big enough that they can easily go around other collisions overall dynamics of the polymer.
So I guess if what you're saying is that if it's a stiff chain,
Yeah.
then it's easier for it to go straight as opposed to it's a flexible chain. Then
Not in this. In this, generally a stiff chain flexible because of the active force rule we have, because the active force is proportional to the total active force. And if I have a stiff chain, it's a more like end-to-end vector is bigger, so overall it goes faster. But effect of periodic packing fraction. But what you say is true for have a higher packing fraction. I'll show you in a minute. And here I show you the results for the case of a strong conform is 60% packing fraction. And then here we see, as you expected, very distinct dynamics for the flexible. You see they are I'm working with 4 network model in a flow, and it's exactly there, like you have throats nodes for deriving, and then here you have they open up, and in the other case, as you can see, they most of the time go straight in the channel, so they become like, and then so sometimes they turn. I don't know if you saw any turn.
yeah, no,
Yeah, because I only repeated them. And so let me go. Okay.
Can you show it again? I didn't see the rectangle.
Yeah, I was talking. I did put those at the same time. Caging is the flexible case when they are stuck in the nodes of the network.
there.
And then they go to another case. You have a sequence of cage and hopping. In the other case, in the narrow channel, and every now and then channel switching. Yeah. And if you look at effect of it for as a function of activity for the same, actually I have shown here for all the packing fractions we had free space 20%, 60%. The dependence on active force for the free and low packing fraction of obstacle is not so dramatic, it's something not so significant. But what is interesting, if you have a strong conformer, you have to cage them, so you have much smaller polymer size and to a distance. And if you have high enough activity, this seems to overshoot, and at some point you just transition, but we haven't analyzed it from the view of dynamical case transition.
That I don't understand because your active force is acting along the end-to-end vector. So therefore, if you're increasing the active force for a very straight chain,
Yeah.
then why should that increase the frequency of these startings?
Because active force one vector.
Yeah, but so if it's almost a straight chain, then the active forces are acting along.
Yeah, but it's in this case
That's
there's
okay.
no
For the flexible case, oh, I'm sorry.
in this you can see that when I have very strong confinement, the fact that it suffers fluctuations. Because it can overcome the bending stiffness basically, and then our cases it's not exactly, but it's approaching the free space limit when I go to activity. So somehow with activity you can overcome. It's what we see to overcome the barriers. And so I go to the next, and I think it was nice if you look at the effective persistence. Again, it's not the intrinsic persistence is checked. You can see for the stiff case, the persistence is going down with activity. Okay? The one which is you calculate from the one correlation function. And for the very high packing fraction. And then I thought it's worth to discuss like dynamic. In the case, this is just a end-to-end set of for a typical activity and a flexible one. You can see it's like another case you see is a lot of time almost constant, the same as almost very narrow channel. With the mean caging time of activity. Is when we and the mean caging time becomes a smaller recipe. And here the same. And so. And then we look at also the orientation of end-to-end vector. I took the end. It's almost exponential. It seems to be like the rotational relaxation time of. And this is what I have shown. And as you can see again, for low activities, when it's caged, you have a smaller reorientation time, but when you go to high enough activity, it's still going lower, but it's just approaching the free space limit. And what is interesting, orientation. The case of passive one. Maybe I'm going to be much detail about how much time I have. I think over. Okay, so I only focus point rising, and you can the intuition that they go.
Do you always see long-term clean diffusion, or do you see different exponent fractional if you?
No, we have implemented, but
Yeah.
I didn't show it, but I can show you later. We are writing a draft. So in most of the going to the lifetime diffusion,
Yeah.
only in subdiffusive regime, and just it's work, ongoing work with experiments. I don't know exactly how to do better job to see if the model fits. Because they seem to have the head which has some preference, it's not fully tangential. And they see is that with increasing packing fraction, there is a small decrease of line time diffusion. For us, this is almost constant. So the turn, so we are still working because we need better. I think you can go because here is I have shown this is a line time diffusion here, and the line time diffusion here is not changing much with the packing fraction. So these are the different. Actually, sorry, I made it. This is not copper. This is different phi. Last minute preparations. This is different, and it's for phi data are almost phi active forces. So we don't see that, but for them also the decrease of line doesn't seem to be huge. So maybe in that sense the flows are similar. So I just actually and repetition is it has been autocorrect. I see. Formation as free space basically. So I think this was remarkable that by activity you can overcome applications even if you are in confined environments. And I think I skipped that. This is for question. I just want to finish. This was a nice work at this. We are simplifying this as theoreticians. We want to know what's the effect of this active phenomenon when obstacles are movable. And I just end up by I find it cool with the patterns, the worms you see in the soil. I guess it is.
Oh, okay, okay.
I think this was a yeah, it's even for this, but here you get a spiral.
I feel that way sometimes.
Yeah. Actually, I don't. Wait, you see what you see? Because I saw some done the farm open up. In this case, the spiral is a rare event because we and opening up. We are gonna look at it as a rare event also in another project. And I don't know if you'd like to watch more. As you can see, there is a hexagonal
Yeah,
here,
yeah.
and she quantified. I was impressed for 3 months. She's a great bachelor student, you know. So she looked at the distribution of local hexagonal order parameter at the start, and at the end, you can see there are clearly peaks appearing, it's becoming dominant at the large. So this is the average Q6
Okay.
as an active force. So it's not so sensitive. An active force is not good. That's true. But this is very preliminary, so the fun thing. And with it, I would like to thank people who contributed to this work, especially Mohammed and Yen. And thank you for your attention.
Your experimental colleagues and your simulations explored worms in a grid-shaped array of pillars, but that also really does focus the worms onto a single track unless they have enough, fluctuation or a lack of stiffness to replicate. But of course, in the natural world, as you saw also in the final movie, we don't find grids in soil, and I could imagine that having a random array of posts can really change, especially a lot of the timescales and the dynamics that you find.
This we have done first. I didn't have time, so actually this work experiment, so it's very interesting. This experiment is quite. I was going for job interview. I told them about active polymer and fire ants. And oh, we can't reevaluate worms because they're like active polymers. So the other way around. And this was. Oh, I can make pillars. So he had show it because it seems I didn't want to show that something simulation And it's on my data, so I also that it's decreasing. So that tells us that the I just and it seems to be good. It's developing better, like a time-dependent active force moving around the country. Maybe this answers the question, but this regular model we cannot explain. But they have done. But now that you told me, I can simplify. I didn't have time to make consistent with my notation. Activity measure is different. And at the intermediate it's like sketch dynamics, but they don't see anything like what we saw, that you get this channel suit, but they can see also enhancement of diffusion for the C polymers are diffusive for them. For us, it's more controlled. Yes.
In your thinking with the worms moving around,
Yeah.
what's the interaction between the particles?
You mean in this one?
Fine.
Yeah, they have just been like a WCA potential, like just
But then if you have frictional interaction, they can shift the jam.
exactly.
So this would be like quicksand. And so
Yeah.
all kinds of other interactions.
I agree that it was a fair. But we haven't done it. It was just a start. We found that funny, and I agree that we need to do it. And I think that's more realistic. I should focus again.
Because the moment you can't reach it.
Yeah. Yeah, your average just didn't have time yet.
Speaking of friction, you would with your pillars, would you need some sort of pair dissipation or pair friction, and could it possibly matter?
That I because in the solar one, the biggest
okay,
conflict
yes,
we have is for the solar. Because maybe they are not like this active polymer model, but there are some at the same time. But you need to
Maybe you
investigate more.
Maybe you can introduce memory in your equations and then.
Yeah. Oh, that's it's more advanced. Yeah, I mean, more and more realistic. Yes.
I should mention that the other program have a lot of people who are experts on anomalous diffusion and things like that. So you should probably talk to people.
Which one there are four?
The mathematics of movement program.
Oh, yeah. Thanks. That's good. Yeah. I should probably catch them. I was starting to read more and more
Sorry,
about the anomalous diffusion. It's funny actually with this caging and fractal dynamics. Yeah.
Do the worms have eyes? Can they actually see obstacles?
I think they have, but let me ask. I think they should have. But yeah, that's a question: how much the intelligence of them matters, or how much is like really self-driven, naive modeling.
Okay, I think we're out of time here, so I mean you're on for the next couple of